This is a tutorial that's going to review the concept of electronegativity and how electronegativity determines the type of chemical bonds we have in a compound. When we have compounds that are classified as ionic, what we have is complete electron transfer between one element and another in a compound. One of the elements is going to have a low ionization energy, which means it will easily give up electrons. One element will have what's referred to as a high electron affinity, or a very energetic ability to acquire electrons during chemical reaction. When we have compounds that are covalently bound, electrons are shared in molecules, and typically we have two elements that both have high electron affinities, and both are eager to take electrons, not to give them up. And then finally, we have metallic compounds, uh, which are sometimes referred to as having a sea of electrons between the nuclei. These are typically two elements with very low ionization energy, and electrons can very easily move in the solid. When we take a look at the physical characteristics of compounds that have these types of bonds, we find that ionic compounds typically have very high melting and boiling points. Covalent compounds have low melting and low boiling points. And metallic compounds have both good thermal and good electrical conductivity. All of these concepts are based on valence electrons. Where in the periodic table do we find elements that have low ionization energies? I'll leave you to go back and review that. Where in the periodic table do we find elements that have high electron affinities? Well, we'll review that during this tutorial. But both of these concepts are controlled by Coulomb's law, which relates the energy of attraction between positive and negative charged entities, whether they're nuclei and electrons, or different parts of molecules that has positive or negative charges. Well, let's focus in on covalent bonds and molecular structure. Covalent bonds are referred to as directional. What we mean by directional is that the electrons are found between the two nuclei in a specific spot, and the position of those electrons is holding those nuclei together. This is very different than ionic compounds or metallic bonds, where those electrons are not directly located between the nuclei. Ultimately, we'll find out that this directional feature of covalent bonds determines molecular shape, but we'll talk about that in subsequent chapters when we talk about molecular shape. The directionality of these bonds ends up affecting many of the physical properties we see in the laboratory. Things like melting point, boiling point, and solubility in different types of solvents. All of these are determined by interactions between molecules where every atom has completed its principal quantum shell, or N number. So again, rule of octet. And if we take a look at water molecules, in random orientations, so we've got them here. And what we see is both the hydrogens and the oxygens in water molecules have completed their principal quantum numbers. For hydrogen, that's 2. For oxygen, that's 8. And the only interactions we can have are very low interactions between the hydrogens, which are partially positively charged, and the oxygens, which are partially negatively charged. How do we know that this is the case? We know this because it takes relatively little energy to boil water to separate individual water molecules from each other. Well, how do we know that these are low energy, and what energy are we talking about? Well, this is ultimately determined by the concept of electronegativity, which is what we're reviewing in this tutorial. Well, if we talk about the property of covalent bonds, what we're talking about is a bond that's formed between elements that have two different nuclei, and those nuclei have different Z effective. All right, so if you have trouble remembering what Z effective is from previous tutorials, I suggest that you go back and review that concept. But if the Z effective is different between two nuclei, when those nuclei go to form a covalent bond and share electrons, those nuclei attract those shared electrons at different energy levels, and that's going to determine the distribution of those shared electrons and the distances between those shared electron in the individual nuclei in the elements forming a bond. Electron affinities, if we go ahead and take a look at them in relationship to the periodic table, look like this. We can see as we get to the right end of the periodic table, electron affinities, or the energy attracting electrons, goes up dramatically as we get to the right-hand side of the periodic table and as we rise in the periodic table. Excuse me. And the electrons are seeing an unequal Coulombic attraction, the attraction between positive and negative charges between the two nuclei. The nuclei with the higher Z effective, found to the right and in the top of the periodic table, attract those electrons more strongly than elements with a low Z effective. The pattern that we're going to talk about with electronegativity is similar to what we see in electron affinities, but not exactly. So let's see where the concept of electronegativity is going to take us. And when we're talking about electronegativity, the first thing that we need to hear is a word from our sponsor, who is Linus Pauling. Linus Pauling received his bachelor's from OSU in 1922, and his first major theoretical and experimental discovery surrounded electronegativity. Linus Pauling received the Nobel Prize in Chemistry in 1954 for the development of the concept of electronegativity and how it explains electron distribution inside of chemical bonds. Linus Pauling then very famously also received the Nobel Peace Prize in 1962 for his anti-nuclear weapon activities, and remains the only person in Nobel history who has received two solo Nobel Prizes not shared with any other individuals. A very famous quote that I always like to talk about from Sir Isaac Newton: if I have seen a little farther, it is by standing on the shoulders of giants. In using the concept of electronegativity, we are standing on the shoulders of Linus Pauling, certainly a giant in the history of chemistry. So if we talk about electronegativity, which is the ability to attract electrons in a chemical bond, and examine that concept in relation to the periodic table, what we see is metallic properties, the ability to give up electrons, increases as we go to the left and to the bottom of the periodic table. Electronegativity follows exactly the opposite pattern. Electronegativity, as we go, increases as we go up and to the right in the periodic table. You'll notice that we don't extend that area into the noble gases, which are typically unreactive. And where we find the highest level of electronegativities in the periodic table is as far to the right and up as we can get in the periodic table, not including the noble gases. And we see that oxygen and fluorine have the highest level of electronegativities, and when they form bonds with other elements in the periodic table, are the ones most likely to grab electrons and hold them even in covalent bonds. So if we take a look at the effect of electronegativity on bond polarity, we have to ask the question: when we form a covalent bond, when we're sharing electrons, where are those electrons going to be found? Well, if we take a look at the first two electrons between nuclei forming covalent bonds, and take a look at the Lewis structure for a simple molecule like water, we'll see that oxygen comes into this bond formation with 6 electrons. I've conveniently shown the oxygen electrons in red. No, oxygen electrons are not red. There's no color associated with electrons. We're just designating those by color so we can keep track of them. And each hydrogen in forming its single bond to oxygen contributes 1 electron. If we go ahead and evaluate principal quantum numbers, we see that hydrogen has achieved a complete principal quantum number n equals 1 by sharing 1 additional electron with oxygen. Oxygen has achieved a full principal quantum number of 2, which is 8 electrons, by starting out with its 6 valence electrons and then sharing 2 electrons with those hydrogens. Are those shared electrons exactly in the middle between the hydrogen and oxygen nuclei? Well, the answer is no, they're not. If we take a look at the electronegativity values from the previous periodic table, we see that oxygen has an electronegativity value of 3.5. Hydrogen has an electronegativity value of 2.1, which means that those electrons are going to spend time closer to the oxygen than they will with the hydrogen. If we go ahead and try to designate these symbolically in a molecule, we'll use a small Greek delta to indicate not a full charge, but a partial charge. And then we can see inside of a water molecule, the oxygens carry a slight negative charge, the hydrogens carry a slight positive charge, meaning that these bonds are polar. And if we went ahead and actually substituted in our quantum mechanical electron cloud probabilities, what we would see is an asymmetric distribution as shown here, where we expect to, on a probability basis, we expect to see that those electrons are most often found closer to the hydrogen, I'm sorry, closer to the oxygen, and less often found close to the hydrogens. Well, if we actually calculate the difference in electronegativity, we find that the difference between those two elements is 1.4. And that falls into a range where we will say that this bond has both positive and negative poles. And we have a negative pole of the molecule located where the oxygen nuclei is, and a positive pole kind of collectively where the 2 hydrogens are. This bond polarity controls what we'll learn to call intermolecular interactions when we get to that topic later on. And polar molecules, because they have partial positive and partial negative charges, are attracted to each other, again by Coulomb's law, which controls the energy of attraction between positive and negative charges. Those charges do not have to be full integers, +1, -1, like we would find in ionic compounds. They can be fractional charges, which is what we find for most of our covalent molecules. So these covalent bonds that we've just formed we'll refer to as polar covalent bonds, because the covalent bonds have asymmetric positive and negative charge distributions. So if we have a molecule like hydrogen fluoride, indicated here with our Lewis structure, we would expect, because the electronegativity value of fluorine is so much larger than hydrogen, we would expect those electrons to spend more time closer to the fluorine nucleus than the hydrogen nucleus. And again, if we substitute in our quantum mechanical electron cloud probabilities for those 2 little dots that we put in for our Lewis structures, we would expect on a probability basis to find our electrons more often closer to the fluorine nucleus than the hydrogen nucleus. Our delta electronegativity here is 4.0 minus 2.1, which gives us a delta electronegativity of 1.9, indicating that a hydrogen fluoride molecule has a higher electronegativity or is more polar than a water molecule, which we saw on the previous slide, has an electronegativity difference of 1.4. So again, we're going to designate, as we draw these molecules, a partial negative charge and partial positive charge, depending on the asymmetric distribution of the electrons in that molecule. A molecule with separate positive and negative centers is referred to as a dipole and has a dipole moment, and we'll show that symbolically by showing an arrow starting in the location of the partial positive charge, with the arrow pointing in the direction of the partial negative charge. And just for a little extra on that arrow, we'll put one more line showing a kind of a cross where our partial positive charge is, with the arrow pointing at our negative charge. We'll be able to calculate that dipole moment as in the equation shown here, where Q has the magnitude of charge separation. R is the distance between that charge separation. The larger the distance between positive and negative centers, the larger the dipole moment. This calculation has units of debye, which is a capital D, and debye is 3.34 times 10 to the minus 30th coulombs, which is a measure of charge, times meters. Ionic compounds have dipole moments typically in the range of 6 debye. Polar compounds will find generally in the range of 1 to 2 debye, and nonpolar compounds will have dipole moments of 1 and below. Okay, so dipole moments are a measure of the difference in electronegativity and that charge separation. Our reference values are measured in the gas phase. If we take a look at the different types of molecules that we might find, the difference in electronegativity and the dipole moment, what we'll see is diatomic molecules where we have the same element bonded to itself, like chlorine, because we have two identical nuclei, identical elements. The difference in electronegativity is 0. Our dipole moment, by definition, is 0. And that bond classification then is covalent. If we take a look at molecules that have different elements and different electronegativities, we'll see the difference in electronegativity between chlorine and fluorine is 1. It has a dipole moment of 0.88, and we would probably define this as polar covalent. If we take a look at hydrogen fluoride with a dipole moment of 1.9, I'm sorry, a difference in electronegativity of 1.9, a dipole moment in the gas phase of 1.82. This is polar covalent, and this molecule is more polar than the previous one that we've taken a look at. So generally what we're looking at to define a molecule as polar covalent is an electronegativity difference between about 0.4 and 2. It would be interesting to note, for those of you who are interested in organic chemistry, that the dipole, that the difference in electronegativity between carbon and hydrogen is less than 0.4. In fact, it's around 0.2. And hydrogen carbon bonds are defined as nonpolar. If we take a look at a compound like lithium fluoride, electronegativity difference of 3, a dipole moment of over 6, and that molecule then would be classified as ionic, which means we consider that electron as having been entirely transferred from our alkali metal, fluorine, to our halogen. It's alkali metal, lithium, to our halogen, fluorine. So we've got complete electron transfer there. In general, we have the ability to calculate a percent ionic character, which is the measured dipole divided by the dipole we would get if we completely transfer that electron from one element to another. If we calculate that value for hydrogen fluoride, we see that HF has a percent ionic character of about 30%, 29%, which classifies this as polar covalent, not ionic. Basic rule of thumb, again, rule of thumb, is we're going to classify a compound as ionic if that ionic percentage is higher than 50%.